Hello, Dr. Bauer again for section 3.1 on algorithms. Um, First of all, various problems arise in computer technology and discrete mathematics that are best solved by constructing a model that translates a problem into mathematical symbolism and context. Now, often a sequence of steps is necessary to solve the problem. So when a sequence of steps is involved, this is known as an algorithm. An algorithm is simply a sequence of steps to accomplish some purpose or solve some problem. So a definition, an algorithm is a finite sequence of precise instructions for performing a computation or for solving a problem. All right. So there's some things I can say to help you start to be able to build an algorithm. But it's not an easy task. It's kind of like proofs. It involves thinking and putting together things and knowing how to do certain things. So I'll try to help you as much as I can to be able to build an algorithm. So here's an example. Suppose you have a random string of 99 integers. So you've got this big long list or string of 99 integers. So I have an example here: 157, 88, 240, 416, 93, 318, 35, etc. So you wanted to program a computer to find the largest number in that string of integers. So what steps would you use? Okay. So first, see, the computer can only store two things at a time, or compare, I should say, two things at a time. Uh, it can't look at a string like we can and kind of, with our eyes see which one's the largest. It has to look at them two at a time. Okay, so first you need this computer to store the first number you're considering. Then you're going to compare the next number to that first number. Now, if the next number is greater, then you're going to store that next number as the new number instead of the first one. If not, you'll keep the first one. So, like for example, if the first number is 157, and then we'll compare, is 88 greater than 157? No. So we'll keep the first number, 157. Right? Then it goes to the next number. You look at 240, which is the next number in the list of those integers I gave you. So is 240 greater than that number 157? Well, yes. So then it'll make 240 the number that we'll be comparing to, and we'll look at the next number, which is 416. Now, is 416 greater than 240? Well, yes. So it'll change 416 to be the number that we're comparing everything to. So that's how a computer would have to go through the list and decide which one is the largest number. So as far as a solution in what is called pseudocode, well, first you might want to think about it in terms of normal English, and then eventually get to the point where you can write it in a pseudocode, which is commands that are similar to coding language. So the solution I have here is set t equal to the first number. So t is sort of the temporarily the largest number. So t, I let the letter be t because it's sort of a temporary storage of the largest number. All right. So we set it equal to the first number. Then if the next number is greater than t, we'll change t to be the value of that second integer. Then we'll go on to the third and compare the third. Is the third greater than t? If it is, then we'll change t to be the third one, and on and on and on and on. Whenever it finds one that's greater than t, it'll change t to be that new greater number. So it'll stop when there's no more integers in the string. So then at the end, t will be the maximum integer. So you might want to look at page 192 to help you kind of see this. So let's look at that algorithm in what is called pseudocode. So in pseudocode, we often start with the name of the procedure. Now, an algorithm in pseudocode and in a lot of languages is called a procedure. And so we announce the beginning of this procedure or a little sub program. And then we give the name of the procedure. And then sometimes there are inputted integers into the procedure, that integers that are loaded into the procedure so it can work on those integers. So that's what the A1, A2, dot, 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 AN, A sub n. It's basically telling the procedure to input those integers, and then it tells what type of variable or what type of numbers those are. All right. So then we input the integers. So that's the first line, and then instead of t in the previous slide, I'm going to use max. So the variable max is set equal to A1. As my note says, max colon equals A1 sets max equal to the first value A1 that is inputted from the integer list. All right, then for I becomes equal to 2 to n. That's how to read that. So this is a for-to loop, and a for-to loop has an index variable, so I use the letter I. So for I equal to 2 to n, so what it'll do is go through and let I equal 2 the first time, and then I will be 3, and then 4, and then 5, all the way to whatever n is. All right? So then notice how the next line is indented. It's indented because that is inside the for-to-do loop. Anything that's inside the loop is indented as it's part of that loop. So what it does, it compares if the maximum integer, which it starts off as the first integer, is less than AI. Now what is I? Well, the first time around, I is 2 because I starts at 2. So we're going to compare max. Is it less than A2, which is the second integer in the list? So if max is less than A2, then that means that A2 is greater than max. All right, so then it sets max equal to A2. So in other words, if it finds that A2 is greater than max, or max is less than A2, then it'll set max equal to A2. All right, and then of course and then it goes to the next loop of the loop, next iteration of the loop, then I will be 3. Okay, if I is 3, then it compares max. Is that less than I3? And if it is, then max will be set equal to I3. And so it just keeps going through the whole list all the way to the nth integer, A sub n, A sub n. All right, so it'll go all the way through, and when it gets done, max will be equal to whatever is the largest in the whole set. Because if it reached a certain integer and then it didn't find any more after that were larger, if all the ones after that were smaller, then whatever that one was would still be what max is, because it wouldn't be setting max, it wouldn't be changing what max is after that. So then the last line, return max, that's basically a way to tell or go back and tell the rest of the program, the main program, what max is. So it just returns max back. So it's the output, basically. It's the output back to the main program. Now, algorithms have input values from a specified set. That's these integers here we inputted at the beginning. They produce output, which in this case was the max, which is the problem solution. They have a finite number of definite precise steps, and they represent correct and efficient solutions. So we're usually looking for the most efficient solution we can have to a particular computer problem. All right. So let's look at a couple search algorithms. Search algorithms involve determining if a particular value X is a term of a sequence. So this is different than finding which one's the greatest. This is looking for a particular value in a whole string or list of terms. Okay, so the first type of search is called a linear search. This is on page 194 in the text, and it compares the value X with each a sub I term of the sequence. A1, A2, A3, all the way to A sub n. So in each case, it's comparing, is X equal to A sub I? And of course, I is going from 1 all the way to n. So you can look at the program, I believe it's algorithm number 2 on page 194, but it performs the command I becomes equal to I plus 1. And what that's doing is adding 1 to what I is. All right. So it'll just keep adding to I, and it'll go through and is X equal to A sub I? If it finds it, then X will equal the location of that element. It'll set X equal to the location of that element. If not, if it never finds it, the location will be set equal to 0. All right. We'll look at a slide showing that in pseudocode. Secondly, a binary search can be used if the sequence elements are listed from smallest to largest. Now, that's a requirement for using the binary search. You've got to have the elements listed from the lowest to the highest, okay, or in lexicographic or alphabetical order if they're not numbers. So the algorithm begins by comparing the number or word or phrase to be found, in other words, the X. It compares the X with the middle element in the list. So it finds whatever the middle number is, and the subscript for that middle number would be this right here, in parentheses, n plus 1 divided by 2, but then the floor function of that, the floor function. So let's say that there was 9 elements, or no, let's say there was 10 elements in the list. 10 elements in the list. So that means n is 10. So 10 plus 1 is 11. 11 divided by 2 is 5.5. And then it does the floor function for 5.5, which would bring it down to 5. So it's the fifth. The subscript would be 5 for that, or it'd be the fifth element would be the middle element in the list. So it's rounding down. So actually, if it had 10 elements, there's no middle number there, but it chooses the fifth one. So if the number is less than the middle element, the search only uses the lower half of the numbers. Otherwise, the search continues using the upper half. So in each time, it's going to cut the list in half and only search in that half of it. And then it repeats this cutting in half process again. Now it takes half of the half and looks only in that section. And so it's narrowing down the search so it does not have to compare X with all the elements in the list. It just is narrowing it down to a smaller and smaller part of the whole list that it has to search. Okay, so I want to trace the algorithm for this. So this is the binary search algorithm. Algorithm 2 is pretty simple compared to this, so I wanted to look at algorithm 3, this one that's more complicated. It's the binary search that we just mentioned. So this is the pseudocode for it, and if you have a problem in your homework, which I think there's a couple problems in your homework that say trace the algorithm for the inputted integer, and then they give you some integers. So if the problem said trace algorithm 3 for the inputted integer 14, so in other words, we're looking for the number 14 in the set of integers 3, 5, 8, 9, 11, 14, 15, and 18. So obviously we can look at that and find where 14 is, but the computer can't visualize and see the number 14 in a list so quickly. So we're writing a computer algorithm to do that. Okay, so let's look at the computer algorithm. First of all, it sets I equal to 1. Now this would be the left endpoint of the search interval. Okay, the left endpoint of the search interval. And then J equals N. Now N is the right endpoint of the search interval. Okay, so it starts off I over here on the left side and J over here on the right side. Okay, now while I is less than J, now we'll be changing what I and J are in this algorithm, because our search will be narrowing to different sections of the list. But we're going to continue this loop, searching loop, while I is less than J. Now, as soon as that's false, it'll stop that loop. So if I is less than J, it'll continue going through the loop. But like I said, as soon as I is not less than J, if I is equal to J or if I is greater than J, it'll stop going through that while loop that's indented. Okay, so then M will be set equal to I plus J divided by 2, and then the floor function for that. So that picks out the middle of the section I plus J divided by 2. That picks out the middle number. And then here's the comparison. If X is greater than A sub M, then it's going to set, so that means X is found in the upper half of the search area. And then, so we're going to set I equal to M plus 1, which means, into the upper half. The beginning of the upper half is where I would be. J, or if not, then J would equal M, which means then we're going to set the end of the search at the end of the lower half. So M is the end of the lower half. M plus 1 is the beginning of the upper half. So it changes what I and J are, and it changes where the search or section is. All right. So then if X is equal to A sub I, then location equals I. So if it actually finds the integer in the list, then the location will be set equal to that index variable I. All right. If not, if it never finds that, then location becomes equal to 0, so that indicates it never found it. Okay, so let's trace using this example's numbers. and try to follow through this, and I'll show you what kind of things you should write for a trace. First, I is set equal to 1 and j is set equal to 8. Okay, why is that? Well, I is always set equal to 1. J is set equal to whatever the number of integers is, which would be n. So 1, 2, 3, 4, 5, 6, 7, 8. There's 8 integers, so j will be set equal to 8. All right. Now, while 1 is less than 8, now why did I do that? Because that's what the while command says to do. Compare I, is it less than j? So 1 is less than 8. That is obviously true. So we'll go through the steps that come below it. So m is going to be set equal to I plus j divided by 2, and then do the floor function for that. So that would be 9 divided by 2, which is 4.5, but then you round down to 4. So m will be set equal to 4. Now that means that we're going to look in the lower half of this, and it picks out the middle of it, and then it checks to see if x is in the lower half or is it in the upper half. So if 14, now that's x, we know that x is 14, that was the inputted number, is if 14 is greater than A4. Now A4, if you look at the list, 1, 2, 3, 4, A4 is 9. So A4, 14 is greater than 9, so then we're going to do the then part. Now if it wasn't greater than 9, then we do the else part. The else is done if we do not find this to be true. So I will be set equal to m plus 1. Now m is 4 from previous, so I will be set equal to 5. M plus 1. We're going to skip, it'll skip the else part because it was true, not false. You only do the else if it's false. And then we'll go and do the while thing again. So now you go back up to the top of the loop and you compare. Is I now is 5. We just set I to 5. Is 5 less than 8? Well, yes, it is. So it repeats those steps. M becomes equal to I plus j divided by 2. So 5 plus 8 divided by 2, which is 13 divided by 2, or 6.5. But the floor function for 6.5 would give you 6. So now m is set equal to 6. So is 14 greater than A6? Well, A6, 1, 2, 3, 4, 5, 6, actually A6 is 14. So is 14 greater than 14? No, it isn't. Then I would be set to m plus 1, but it is not. So the else part is done. So the else part says j becomes equal to m. Well, now j is going to be set equal to what m was. Well, m was 6 in the last line, so j becomes equal to 6. All right, now it compares, it goes back to the beginning and does the while thing again. So is 5, that's what the I used to be, is 5 less than j. Now j this time is 6. Is 5 less than 6? So yes, it is. So now we do this again. M is set equal to 5 plus 6 divided by 2, which is 5.5. And then you round down, so you get 5. So now it says if 14 is greater than A5, now A5 is 11, so I is set equal to m plus 1. Now m is 5, so this will be I set equal to 6. And then now I is 6 and j is 6. See, that's what's happening. I and j are getting closer and closer, and then they eventually become equal to each other. So I or 6 is less than 6, so that's false. So as soon as the while command is false, it stops doing that loop. Now it goes to the lines at the bottom, the 3 lines at the bottom. If x equals a sub 6, all right, well, a sub 6 is 14. 1, 2, 3, 4, 5, 6. Yep, a6 is 14. And is 14 equal to 14? That's true. So the location is set equal to whatever I was, which is 6. And you don't do the else. And then the procedure returns that location. So it will return the output of whatever location is. Well, location is I, which is 6. And so it found the number 14 in position 6. All right, so that's an algorithm, and it's important that you think almost like a computer, that you look at, you know, the variables, each one and what it was before, and then do exactly what the computer program tells you to do. And it's something you got to be really careful with to really understand what's happening with that algorithm. All right, so then there's another type of algorithm called sorting algorithms. Now, sorting algorithms have the purpose of ordering the elements of a sequence of numbers or text. In other words, putting them in some order. It could put them in ascending order from the smallest to the highest, or it could put it in descending order from the highest to the lowest. But there are a couple different several ways to sort the elements in a sequence. Okay, one is called the bubble sort. Now, the bubble sort was invented decades ago, but it's not a very it's a simple algorithm to write. It's a short algorithm to write, but it's very inefficient. It's not the most efficient. It uses a loop inside of a loop. Okay. And here's how I describe it up in this paragraph. Going down a sequence, the algorithm compares the first 2 elements, then the second and the third elements, and then the third and the fourth elements, and then the fourth and the fifth elements. And every time when they're out of order, in the order that you want, if one is greater than the next one, when you want it to be that an element is always less than the next one, well, then it'll swap them. Okay, so if the first item in each pair is greater, then the 2 are swapped. This is repeated in another pass. So you go from 1 to n, and then you go from 1 to n minus 1, and 1 to, you're always going 1 less every time, but you're going through it many times. It's not until the n minus 1th pass. And so that's a lot of comparisons. That's actually n times n minus 1 comparisons of numbers that it has to do, and swappings that it has to do, all right, before it's completely placed into proper order. But as you can read here in the algorithm, it compares a sub j with a sub j plus 1, in other words, the next one. And if a sub j is greater than a sub j plus 1, it'll interchange the 2, and that will make a sub j to be less than a sub j plus 1 instead of greater if it interchanges them. But it needs a double loop. You notice the for loop inside of the for loop? So that's why it's so inefficient, and there's other better algorithms. Now, another sorting algorithm is called the insertion sort. It involves first ordering the first 2 elements, but then inserting the third element either before the first, or in between the first and the second, or after the second. So the same goes for the fourth element. So in other words, you're always going to be, first getting the first 2 elements in order. So you have, the first one lower, then the second one higher, and then it looks at the third one and either puts it before the first, in between the two, or after. So it's always, bringing them in like that, and it's an interesting algorithm, and it's more efficient than the bubble sort. But anyway, so the basic idea is that each element, it looks at where it is and inserts it in the right place, and it gets it all sorted that way. So here is the algorithm, and you'll have to look through at the details of it. I'm not going to take time here, but look down through it, maybe try a sequence of numbers and see how it would work, and trace it through. And that's how you learn. That's how you learn to program, is tracing it through and seeing how it would work to make this sorting of the numbers happen. Hi, I wanted to add a little segment here on different sorting routines, and there's a website, and there's actually several websites that you can look at to compare sorting algorithms. And this is one website I found at toptal.com/developers/sorting-algorithms, and you can see that at the top of the page. And I'll just show this visualization for a minute. So what this is a list of several different types of sorting routines, and there's one called the insertion sort. We mentioned that. The selection sort, the bubble sort, the shell sort, the merge sort, the heap, the quick, and the quick 3. So these are all sorting algorithms, the abbreviated names of the sorting algorithms. And then on the left side is the type of data that it will be sorting in this animation. So random just means that the numbers are randomly stuck in there in the list, and it'll sort that random list. And you can see how the numbers are random, in that some are long, some are short, and it's sort of just, now nearly sorted means that, it goes from lowest to highest, but there's some irregularities. It's kind of from lowest to highest, but it's not quite completely sorted. Reversed means that the data, is totally the opposite. It's in descending order when you want it to be in ascending order. And then a few unique means that there's a lot of them that are the same values, like a lot of 5s and a lot of 13s and a lot of 27s of the same number in the list. All right. So like, for example, the bubble sort, I'll hit go on that, and you see it in action. It didn't take hardly any time at all to do the nearly sorted list, and it was able to do the other ones in more time than that, but it kind of took a while on the random list. Insertion sort, that's another one we looked at in class. It did the nearly sorted real fast. It did the few unique real fast, but it's taking a long time to do the reverse order, to switch it from descending to ascending. So these are, it's pretty interesting. You can hit play all, and you can see which one's faster, kind of have a race of all the types. Okay, see which one will take the shortest amount of time for different types of data. Now, at the bottom of the screen, they can give you the algorithm. So if you want to see the bubble sort, you can click on bubble here, and it'll come to a page that gives you the algorithm. Here's your algorithm right here. It's a little different than we had in class, but it's essentially the same. And then it describes the bubble sort and how fast it is and all that. and you can, watch it in the animations for that particular algorithm. So, you can play with this and look at this to study a little bit more on this. All right. So other algorithms are also beneficial to examine. They mentioned the greedy change making algorithm. This is where, okay, so suppose you had to make change for $1. So someone spends 37 cents and that you have to give them change. So 63 cents is what they get back. So then it's called greedy because you're going to try to find the biggest coin that you can use to give that 63 cents back. So of course the biggest coin would be the $half if you're going to include $half. If you're not, if you're just going to include quarters, the biggest coin would be the quarter. So you give two of those to make 63 cents and change. And so two of those makes 50 cents. And so you have another 13 cents. Well, what coin would you use next if you wanted to use the biggest coins possible? Well, you'd use the dime. You'd use a dime. And so now that adds up to 60 cents. And then you give the 3 more pennies because you can't fit a nickel in just 3 cents. So anyway, you can look at that on page 199. All right. Now, there's something called the halting problem. So back in the 1940s, when computer programming became, the hottest thing, they were just developing computers in the late 1930s and 1940s. So this is how Rosen phrases it. We will show there are unsolvable problems. Did you know that there are unsolvable problems? Now, the problem is called the halting problem. It asks whether there is a procedure that does this. It takes an input, as input, a computer program. So in other words, the input is not numbers, but the input is a whole program, and takes as input a computer program and input to the program, and determines whether the program will eventually stop when run with this input. It would be convenient to have such a procedure if it exists. So certainly being able to test whether a program entered into an infinite loop and therefore didn't have a solution, that would be very helpful when writing and debugging programs. But in 1936, Alan Turing showed that no such procedure exists. Okay, so there's no procedure that we can have to show us whether a program is will halt or will successfully solve a problem. Okay, and so it basically says that there are no unsolvable problems. You can look at page 202 in that respect. Now, that's the end for section 3.1. And, I'll have some program that you have to trace, the output of for, and then I'll have a program that you should try to write a procedure for. And, I understand that you're just developing, some of you, and some have had programming and can probably write programs. Others have not had that much. So I'm just looking for, some growth in that area. And so I'll be somewhat, lenient in the grading of these things. But I want you to try to expand in your knowledge of being able to write algorithms and understand algorithms and trace algorithms. Now, section 3.2 is an extra credit optional thing. And so let me give you the gist of what that is. So when you send a list into a procedure to have it sorted, let's say a list of numbers, and let's say you put it into the bubble sort or the insertion sort or some other algorithm, how long will it take to sort the list? This depends on the number of comparisons that it has to do, because every comparison where it has to decide, is this less than this or whatever, and then swap them, it takes processing time, right? It takes a little bit of time for the computer to process that comparison. So that would depend on the length of the list, because the longer the list you have, the more comparisons it has to do. As I said here, the longer the list, the longer it'll take. But it's not just a linear situation here. In other words, the longer the list, the longer the time it takes in a linear fashion. In other words, you couldn't draw a graph that's a straight line where along the bottom is the amount of numbers in the list, the number of numbers in the list, and the y coordinate is the time it'll take. So it's not a straight line. It's actually a curving situation usually, and often it's an exponential or a power or a polynomial function. Okay, so section 3.2 discusses how long and how many comparisons an algorithm will take to process a list of n items. So this involves the speed of the growth of various functions of n, okay, the number of items being processed. And that depends on what type of function it is. And that's important, because if you have an algorithm to sort some numbers and you want it to do it in a reasonable amount of time, if that speed of processing really slows down when you put a large list in there, you're going to have an issue. You want it to process in a fairly quick way. So you can study section 3.2. I have a page of notes on this summarizing the theorems and facts in the section at the end of the notes for this week. So you can look at that. All right. Well, thank you. Have a good night.